Hey guys, in this video I'm going to be solving the following problem. What is the optimal v vector for the following PCA objective? So in class we learned about PCA, and the high level idea is it's an algorithm we can use to reduce the dimensionality of our data. So um, a simple example would be you have 100 million features and you want to figure out what's the best way to reduce that down to maybe 100 or 2 or 4 features, such that we keep the variance of our data, but yeah, so such that we don't lose too much variance. Um, and just to kind of write out a toy example of that, let's say we have 2 features in our original data set, and we want to figure out how we might reduce it to 1 feature in a way that preserves as much variance as possible from our original data. And visually, it might seem that a line such as this. So like, let's say this is our vector that we project onto. This wouldn't be a very good solution, right? Because once we've projected all of our points onto this line, while it seems that we have, maybe good feature separation, that's probably not the case. Our variance between data points is not, our bounds of our data is actually quite small. So what a better option might be is something like this, where once we project all the points on, we actually have a larger, hopefully that's larger than the original line, larger bounds of data. So with that toy example in mind, I'm going to write out the algorithm real quick for PCA, and then we'll tackle this actual problem. So the first step of PCA is we have all of our original data, and we construct a covariance matrix. I'm going to call this Q, just like it's called up here. And so what this means is, well, if I have D features, my covariance matrix is going to be D by D. And so what that actually looks like is it's going to have D rows and D columns. And each cell in this matrix is going to be the covariance between 2 features. So in this case, this is just variance, and these diagonals are going to be, just variance of each of the features. But here in the upper triangular and lower triangular, we're going to actually have covariance between different features. And so this is in some way to capture, the dependence in some unnormalized fashion between different features. So yeah. So the next step is, well, once we have Q, we need to eigen decompose Q. And so what this means is we take Q and we turn it into our, I'm trying to remember what we call these. So, eigenvectors, I think it's V, and eigenvalues, sigma. And really what this means is, well, Q is equal to V transpose sigma V negative 1. Oh, there's no transpose here. So yeah, so we need to diagonalize Q. The third step is so PCA usually clarify how many new features you want. So in this case, I'm going to say PCA N. So this is how many features we'll have at the very end. So what we do is we choose, sorry, I can't spell, N eigenvectors with largest eigenvalues. And then finally, project. So I'm going to call this V max. These are the eigenvectors with the maximum eigenvalues. Then we're going to project our data onto V max. So this is PCA. This is the PCA objective. For this problem, we already have our covariance matrix Q, so we just basically need to do these two steps. And since the question asked to only find the optimal vector, in this case, n is equal to 1. So easy peasy. So let's tackle eigendecomposition. So if you remember, we have the following identity. So we're going to say, I'm just going to keep Q. Q times some eigenvector V is equal to lambda times V. So basically what this is saying is if we apply some transformation Q to one of its eigenvectors V, well, that's just the same thing as scaling the same eigenvector V by its eigenvalue. So using this equation, we can rearrange this, and we can turn this into QV minus lambda V is equal to 0. And we can simplify that even more, and we get Q minus lambda I. This is just the identity matrix, and I just use I use that here just to turn this scalar into an actual matrix that we can subtract from Q. V is equal to 0. And so here I'm going to put this up here. So this is the equation we're going to be using during our eigendecomposition process. And the basic idea here is if you remember how we've done eigendecomposition in the past, we solve for our lambdas first, and then we use those lambdas to solve for our eigenvectors. And in this case, these are eigenvalues, and these are eigenvectors. So the first assumption we need to make here when we're solving for our eigenvalues is, well, we're saying that, I'm going to get rid of my labels. So in order to solve for these eigenvalues, we basically need to assume that V is not 0, not the 0 vector. Okay, so since V is a non-zero vector, in order for this to have a non-trivial solution, we need to assume that it's non-invertible. If you want more information on that, I would look at our class notes on eigendecomposition. However, using general linear algebra principles, for this to be non-invertible, well, that means that the determinant of Q minus lambda I is equal to 0. So our first step is to solve this for Q. So setting this up, we have our Q matrix here, and so we want to say that the determinant of, I need to look at it again, 2, 1, 1, 2 minus lambda times the identity is equal to 0. And if I simplify this even more, we have the determinant of 2, 1, 1, 2 minus lambda 0, 0, lambda is equal to 0, which turns into, I'm going all over the place, the determinant of 2 minus lambda, 1, 1, 2 minus lambda is equal to 0. If you remember the determinant equation, it's simply this diagonal minus this diagonal, so we get 2 minus lambda times 2 minus lambda minus, and then this diagonal, which is simply 1. It's equal to 0. So if we simplify this out, we get lambda squared minus 4 lambda plus 4 minus 1. It's equal to 0, which if we simplify this out is plus 3. And then, just eyeballing this, we know this is simply this is simply equivalent to, this is simply, I'm stuttering, lambda minus 3 times lambda minus 1 is equal to 0. So lambda is equal to 3 and 1. So if you remember our PCA algorithm, we only choose the lambda with the largest magnitude. So in this case, 3. And since we're only choosing one principal component, so the optimal v vector, we only have to find the eigenvector associated with 3. Okay. So now that we have found our lambda, we just need to find the eigenvector connected to lambda. So now that we have lambda, we can use this full equation right here since there's now only one unknown. So we have q minus 3 times the identity times v is equal to 0. Sweet. So let's do that. Okay, so I got to remember q. So we have 2, 1, 1, 2 minus, I'm just going to skip a step, 3, 3, 0, 0, v is equal to 0. And so if I come down here, I'm just going to do this step right here. So we get 2 minus 3, that's negative 1. 1 minus 0, well, that's 1. 1 minus 0, that's 1. And then 2 minus 3, that's negative 1. So our goal is to solve this system of equations. So just eyeballing it, it seems like the first row is just the negative of the second row. So really we just need to solve the equation. Here, I'm going to simplify this out. And we know v is equal to v1, v2. So really we just need to solve the following equation. Negative 1 v1 plus v2 is equal to 0. And, well, if we just rearrange it, we say v1 is equal to v2. So with this in mind, we know that the eigenvector v associated, so let's say v associated with lambda is equal to 3 is just simply 1, 1. The final step is we just need to normalize it. So we say v of lambda is equal to 3 is equal to 1, 1 minus the times 1 over the L2 norm of this, which is just simply square root of 2. And so this is our final answer. So we have, that is our eigenvector with eigenvalue equal 3. Sweet.